All right, good morning, everybody. So today we're going to get into chapter 16, and we're going to start talking about aldehydes and ketones, of which we've already talked a little bit about, actually quite a little bit about. What have we learned so far that we can do with aldehydes and ketones? We can reduce them and turn them into alcohols. What reagents do we need to do that? Which ones in particular? That's true. LAH will work, sodium borohydride will work, right? Sodium borohydride will reduce aldehydes and ketones, right? Lithium aluminum hydride will do that as well, but also other things, right? So for the topic of this particular chapter, sodium borohydride is pretty good. What else can we do with aldehydes and ketones? How can we convert an aldehyde into a secondary alcohol? Grignards or alkyl lithiums or the alkanides. Remember we talked about those three specific organometallic reagents? Any of those will work. So aldehydes get converted to secondary alcohols upon reaction with the organometallic reagent, whereas a ketone gets converted into a what? Tertiary alcohol, right? How can we make aldehydes and ketones so far? How have we learned how to make aldehydes and ketones? Okay, so I can take a primary alcohol and do what? PCC, oxidize it to the aldehyde, right? How would I make a ketone? Yep, I can use PCC. I can use PCC, but I can use just about any oxidant that we talked about, right? So we only have to really be careful with the oxidant that we use when we have primary alcohols, because we can over-oxidize those to carboxylic acids. What other ways can we make ketones and aldehydes? Ozonolysis, that's right. So we can ozonate alkenes, and we can cleave that carbon-carbon double bond and make either a ketone or an aldehyde, depending on the substitution of the alkene, right? So if we have a highly substituted alkene, we typically get ketones. If we have like a terminal alkene, we will get an aldehyde, right? So today we're going to build upon a lot of this. We're going to talk a little bit about some spectral properties. Nomenclature I'm going to leave to you. You all can do that now. And we'll start talking a little bit about some reactions of aldehydes and ketones. We won't get through everything today, but we're going to start talking about some reactions of aldehydes and ketones, and hopefully we'll get to where we can talk about the nucleophilic addition of cyanide. All right, so if we look at aldehydes and ketones, what you'll see is that we've got, how would we name this one? That's formaldehyde, then we have an aldehyde, and we have a ketone. I think you all will agree as we add more R groups, the steric hindrance increases. And so if a nucleophile has to approach the carbon of the carbonyl, if it's sterically crowded, it's going to be difficult for it to react, right? So we would expect nucleophiles to react very, very quickly with formaldehyde, pretty quickly with aldehydes, and slower with ketones. Now, I say all this, and in reality, the reaction on a human timescale is actually quite fast for all three of these, okay? Ketones are typically quite reactive unless they have a lot of big groups for R around them, okay? But that's typically what we notice, is that aldehydes react faster than ketones because of steric hindrance, okay? We know the physical properties pretty much. If we think about comparing, in this case, an aldehyde with similar molecular weight molecules. So here we have an aldehyde. The boiling point is about 80 degrees, or excuse me, is about 76 degrees, excuse me, right? So we got about a 76-degree boiling point. If we look at something that is similarly weighted in pure hydrocarbon, here we've got about 36 degrees. And then here we have, again, something very similar and a boiling point of 118. So aldehydes are going to be somewhere between hydrocarbons and alcohols. Aldehydes and ketones have what kind of intermolecular forces? Of course, everything has what? Everything has van der Waals. But what do the aldehydes and ketones have that beyond that? They have dipole-dipole, right? They have a permanent dipole. That CO bond has a permanent dipole, and so we would expect then to see dipole-dipole interactions coming to play and increasing these physical properties. Solubility for aldehydes and ketones. Aldehydes and ketones are going to follow that rule of 5. They're going to be soluble in normal organic solvents. You're going to be able to take an aldehyde or a ketone and dissolve it in dichloromethane and benzene and toluene and THF, the typical things. But if the aldehyde or ketone is actually quite small, less than or equal to 5 carbons per aldehyde group, or carbonyl group, I should say, they typically tend to be water soluble. So if you use acetone as your fingernail polish remover, do you worry about it getting rinsed off? You don't, because it's perfectly water soluble. Acetone has 3 carbons and 1 carbonyl. It meets the 5 carbon rule. However, if you used cyclohexanone, it will dissolve the paint, but it's going to stick around because you're not going to be able to rinse it off very well with water. Okay, and so that's why we use small organic compounds for things like that, because you want to be able to rinse them off at the end. Okay. Spectroscopic properties, IR spectra. It turns out that us organic chemists really like to use IR when we're talking about ketones and aldehydes, probably more so than we like to use NMR, which is kind of rare for you to hear me say that. NMR is my favorite tool. But when we're talking about aldehydes and ketones, we really do want to use IR because, number one, the stretches are typically quite strong. Okay? They're diagnostic. And if you think about NMR, there's no protons on a carbonyl typically, right? Unless we're talking about an aldehyde. But ketones typically don't have any protons there. So you have to look at carbon NMR spectra to make sure that they're there. And carbon takes a lot longer to run. I can go run an IR in just a few minutes. How long does it all take you in lab to run an IR? Not long. You're standing in line waiting on the IR longer than it actually took you to run the IR itself, right? And so it's a very quick technique, doesn't take much sample, and so IR is quite good. Where do we expect to see carbonyls? In what region? The sp2 region. Where do we start? 1500, right? Everything to the right of 1500 is our fingerprint region, and so the sp2 region is between 1500 and 2000, right? So we would expect to see a stretch somewhere between 1500 and 2000 for something that contains a carbonyl. And here we've got propanol. It's got the carbonyl. We can see the stretch quite strong right there between 1500 and 2000. So we can get a lot of information really quickly by looking at IR spectra. Okay. Now, we can actually get even more information from our IR spectra. What I held you responsible for in chapter, was it 2 or 3 last semester, where we talked about IR? I can't remember. One of those chapters, right, early chapters, was I told you really only needed to know the ranges. And that's still largely true, but you can actually get a lot more information if you pay attention to the details. So for example, if you look at ketones, cyclic ketones, so here's a 6-membered ketone, a 5-membered ketone, and a 4-membered ketone. What you can see is that the shift changes. Okay, so the 6-membered cyclohexanone is going to be around 1715 wave numbers. The 5-membered ring is going to be around 1745. And this one's going to be around 1780. Okay? What's changing? Well, technically that's true. But those are all numbers. Size of the ring, and what else? The ring strain changes, right? And so as the ring strain changes, what's happening to our wave number? It increases by about what? Approximately. About 30 wave numbers, right? More or less. You're going 30 and then almost 30 there. So as we increase the ring strain of the ring that the carbonyl belongs to, what are we actually doing to this carbon atom? What are we really doing to it? It's moving towards what region? No, it's in sp2, but it's moving closer and closer to the sp region. Why is that? It's being bent more, and it's starting to look more like a more linear, right? It's becoming less and less sp2-like. And sp carbon, right, would be linear. And these things are getting closer to that, right? They're not that, obviously, but they're getting closer to it. And so it starts to have more character like an sp hybridized carbon. Not enough to knock it into that region, but it's just being shifted closer to it, okay? So technically, if you really think about it, the hybridization of this carbon, and this carbon aren't the same. They are slightly different, okay, because of those bent bonds, as Anna mentioned, okay? So we can actually use IR to determine what kind of ring our carbonyl is in. That's very difficult to do with NMR, but we can do it quite easily with IR spectra, okay? And so we can get the functional group, and we can tell what kind of ring it belongs to by looking at this. Still don't have to look in the fingerprint region to do this, okay? Conjugation also affects the IR absorption of the carbonyl. So for example, here we have a ketone, right? But this isn't just your ordinary ketone. This is a ketone that's in resonance with a double bond, right? These are conjugated, okay? And so we can draw resonance structures for this, right? Obviously, we can push these electrons up to oxygen, generate an oxygen anion, a carbocation, which then is in resonance delocalization with the pi bond, and you can end up with these three resonance structures. This is the overall resonance hybrid, okay? And so is this going to have an effect on the position of the IR absorption? You bet, right? It absolutely is, because that resonance hybrid, because of resonance structures, it's not going to be as, quote unquote, double bond-like, if you will. So here we have this ketone. It is not in resonance with anything. It's just a ketone. It appears at about 1709 wave numbers. That's kind of where you would expect to find a typical ketone. Here we have a ketone, but it's connected to an aromatic ring, which gives it resonance structures, right? Notice what happens to the wave number. Does it go up or down? It goes down, so it's shifting to the right or to the left in the spectrum. It is shifting to the right. And the right is what? sp3. We called it the fingerprint region, but it's really the sp3 region, right? Why is it shifting that way? Okay, yeah, if we look at these resonance structures, right, this resonance structure starts to look more and more like an sp3 hybridized carbon. It's got a carbocation on it, but it's more like a single bond, right? And so there's more single bond character in this carbonyl than in this carbonyl than in this carbonyl. And so it gets shifted a little bit to the right, to lower wave number. And so if you look at cyclohexanone, 1715, if you look at the conjugated version of cyclohexanone, where we got this alpha-beta unsaturation, it goes down to 1685. Okay, so it's about, again, approximately 30 centimeter, reciprocal centimeter or wave number shift to the right. All right. So NMR is also very important in carbonyl-containing compounds. Obviously, we have two types of NMR that we're going to be interested in here, proton NMR and carbon NMR. I would argue that for the most part, carbon NMR is probably more important for the carbonyls because they have very distinctive shifts, chemical shifts in the spectra. Proton NMR is useful, but you get a lot of information from the C13. Okay, so on an aldehyde, that hydrogen that's attached to the carbonyl carbon, it's going to be highly deshielded, and it's going to appear somewhere around 9-ish, 10-ish. Okay, that's way far upfield or downfield? Downfield, right? That's way far downfield, and you'll see a peak there. Okay. Now, if you have alpha protons to that carbonyl, you will see coupling to that, but the coupling is quite small. Usually about 1 to 3 hertz is the coupling constant, and that's so small that sometimes it'll still appear to be a singlet, depending on how well the NMR machine is running that you're using at the time. Okay, so remember, coupling is how things split, right? So remember, if we had a proton that had two neighbors, what was it split into? is split into 3 peaks, and those peaks were separated by a certain amount of what we call hertz, and that's the coupling constant, okay? And it turns out that in aldehydes, that coupling constant is quite small, okay? So in the carbon NMR, again, you have a lot bigger region that you're dealing with, but you're going to find the carbonyl carbon somewhere between 190 and 200, 215. So if you see anything out that far, you can bet it's some type of carbonyl, okay, typically. Okay, so anything around 190 to 200 or so is typically going to be a carbonyl-containing molecule, okay? So here's some examples. So how would we name this? How many carbons do we have? We have 3 carbons, so it's, what's the parent? 3? Prop, right? And what's the functional group? It's an aldehyde, and how do we name an aldehyde? We drop the A-N-E ending and add Al. This is propanal, okay? So we have propanal. We have 3 unique proton environments, HA, HB, HC. And so A is how many protons? 3 protons. Are they going to be way upfield or way downfield? They're going to be the upfield ones, right? Because they're the furthest away from the carbonyl, right? They're sp3 hybridized, so we would expect them somewhere over in here, round 1, and there they are. And it's going to be split into a triplet. Why? It's got 2 neighbors, right? Now, CH2, okay, the CH2, which is HB, right? How many neighbors does it have? It's got 4, right? But notice it's appearing like a quartet. Something's wrong there, right? If I have 4 neighbors, how many peaks should I have? I should have 5 peaks. I should have 5 splittings. Does that look like a typical quartet? It's a little lopsided, isn't it? This peak's a little taller than that one, right? It turns out that it is coupling to this and to these 3. It is actually coupling to all 4. But what's the coupling constant for this hydrogen? Big or small? Really tiny. So we're not able to see the coupling to it very clearly, okay? And so, but we can see the coupling to these 3 because the coupling constant is quite large very easily, okay? And so it still appears like a quartet. So aldehydes can kind of mess with some of the rules that we learned about in NMR, okay? But it's not too bad. And then HC, the aldehyde, it's out here around, what would you call that, about 9.8 or so, maybe 9.7. It appears to be what? It looks like a singlet, but it really should be a what? A triplet, because it's got 2 neighbors, right? But again, the coupling constant is so small, we can't really see it very well, okay, on these low-resolution instruments. To actually see that, you would actually need to use a higher resolution instrument, something like over in the polymer building. They've got a 600 megahertz NMR, and you'd want to see it there. My guess is this was probably run on something like a 300 megahertz NMR, and you're probably not able to see those couplings very, very clearly, okay? So the coupling is there, but you can't always see it, okay? So what do we see here? Does this make sense? So this is a what? Hydrogen? Carbon? C13 spectrum?
That was the last one we did was hydrogen.
Last one we did was proton. Hydrogen, yes. Right. So we see the 3 carbons. Anything strange about the height of those? Okay. A and B are taller than C. It can mean that they're integrated more, but what did we talk about being able to integrate carbon spectra? You can do it technically, but it's not common, okay? It's not a common experiment that we do. So here the peak height does not tell us anything about the number of carbons, right? If I look at this, there's just as many sp2 hybridized carbons, right? Let me rephrase that. There's just as many C carbons as there are B carbons as there are A carbons, right? So if we had a mole of propanol, there would be a mole of C's, a mole of B's, and a mole of A's. They should integrate to the same thing, but they don't. Can anybody tell me why they don't? It is very deshielded. That is a true statement. It is connected to the oxygen. That is a true statement. What else is different about them? How many hydrogens are attached to C? And how many are attached to A and B? More than one, right? And it turns out that in carbon NMR, the number of protons that are attached have an effect on the size of the peak, okay? For reasons we don't need to get into. But you don't need to think that this has an integration that is smaller. Remember, we can't accurately integrate carbon-13 under normal conditions, okay? There's other experiments that we can run that do that, but not here, okay? Not in this class, okay? So, two spectra, two molecules. Match the spectrum to the molecule for me. What's diagnostic? Do I need to interpret all the signals to answer this question? Nope. What could I do? You're talking about here? Yeah. Okay, so you're looking at these? That's not a bad thought. That works. A little more complicated, though. What's the easy thing to do? Look at the one that is way downfield, right? So if I look at this, that is split into a doublet. You can kind of see the second peak there. That is split into a what? A triplet. Now, can we make a better prediction? Which one does this belong to? This one belongs to this? The top one? And why? Because we've got this hydrogen coupling to those two, and that should give us a triplet. And it's kind of hard to see, right? But it's there. And so on an exam, I would probably have blown this up for you so that you could clearly see it. We didn't have to go through and add everything up, right? We looked at those diagnostic peaks, and we were able to make a decision based on that, okay? Now, the way that Jack was going about doing it would have worked just fine, looking at these characteristics peaks. So here's 6 protons that look like they're split into a doublet. That's got to be these two methyl groups right here. They're equivalent. There's a hydrogen here that splits them into a doublet. Anything that integrates to 6, because I know I can't have a single carbon with 6 bonds to it, means that I got to have 2 groups that are equivalent. And that's the only one that gives me that, okay? All right, there are some aldehydes and ketones that you all are familiar with, whether you know it or not. For those of you who like to cook and for those of us who like to eat, these molecules are actually quite useful to us. So citral, this molecule is what functional group? That's an aldehyde, but is it a typical aldehyde? It's conjugated, right? So we've got this conjugation. So we would expect then that its IR peak would be shifted to the left or to the right in the IR spectrum. To the right a little bit. By about how much? 30. By about 30. Yeah, we'd expect, compared to a regular aldehyde, we'd expect this to be shifted to the right a little bit by about 30 wave numbers. This molecule right here is responsible for that lemony odor that people like to have in some of their foods. So they will use lemongrass, and you can actually use that in your cooking, right? And it gives it that lemony aroma. A little bit of flavor gets imparted on because of that, and you end up with a tasty dish. Cinnamaldehyde, what's kind of unique about this one? Yeah, so we've got conjugation, but it's conjugated not only here, but also through here, right? It's highly conjugated, right? And so we might even expect that its IR spectrum to be shifted a little further to the right because of the extent of conjugation, right? This is the odor of cinnamon. So for those of you who like those little car freshener kind of things, they don't actually use real cinnamon unless you buy the organic ones. The synthetic ones, they basically just put a little bit of cinnamaldehyde on some kind of, substrate that absorbs it and lets it slowly evaporate into your car. So, cinnamaldehyde. And what? Never mind? Just kidding? Okay. All right. Benzaldehyde. If you like the smell of cherries, I do. You're smelling benzaldehyde. That's one of the things that's giving you that fragrance. And in fact, in our laboratory, we have a big bottle of benzaldehyde, and I know when my graduate student has been sloppy with it, because I'll walk in and it smells like a cherry parfait. I mean, it has that cherry smell. Quite frequently, he'll get some on his glove and just take the glove off and throw it in the trash, and it smells good. So I don't really complain too much. It's not like the other things that he typically stinks up the lab with, so I don't really worry about that one too much. But cherries and almonds kind of get their aroma from benzaldehyde, which is a very small molecule, very volatile, and that's why we can get the odor very well. 2-heptanone. These three were obviously aldehydes. Here we have a ketone. This is what gives blue cheese its odor. Okay? How many people like blue cheese? A couple of you, right? Some people don't. A lot of people don't like the odor. And it's because ketones typically have this blue cheese, musty kind of smell, whereas aldehydes have more of a fruity kind of odor that's associated with them. So more people typically like the aromas that you get from the aldehydes, while there are some of us who like the more ketone type smell. Okay, so but it's a very simple ketone. Odor of blue cheese. All right, so preparation of aldehydes and ketones, we've already talked a little bit about this, but it's good to go over it one more time. Primary alcohols with PCC can give us aldehydes, right? There were some other oxidizing reagents that were talked about in that chapter that we didn't go over explicitly, but you need to go back and study them. It is the Swern oxidation. They're named after a guy named, last name was Swern, okay? The Swern oxidation does the same thing as PCC. The bad thing about the Swern oxidation is the byproduct stinks like no tomorrow. And so a lot of people will avoid the Swern oxidation and use PCC. So go back and read up on the Swern oxidation. We can also make aldehydes by reduction of esters or acid chlorides. So we can take an ester and we can reduce it with this reagent, dibol, or dibal, depending on who you talk to. I call it dibol, okay? Or dibol H. Anybody know what dibol stands for? What do you think the D stands for? Di. Iso, butyl, aluminum hydride. Diisobutyl aluminum hydride, dibal. It has one hydrogen attached to the aluminum, okay? And so if you are careful, you can reduce an ester at low temperature to an aldehyde, okay? It will, however, if you add too much dibol, reduce the aldehyde all the way to the alcohol. And so on a practical note, dibol reductions are not for the untechniqued, untrained, okay? You have to do this at low temperature. You have to add the correct amount of dibol, and you have to make sure that it doesn't get too hot, okay? So it's a technical challenge for the young chemist, okay? But to the seasoned chemist, to the one that has a lot of technique ability, it can be done. You can actually reduce the ester all the way to the aldehyde directly. Now, having said that, what's a more practical way for you all to make an aldehyde from an ester? I'm not going to give you all dibol because I know you'll mess it up. You don't have the technique yet, right? But I still want you to make the aldehyde from the ester. How can you do it? Without going this route. How would you take this to this, knowing what you know now? Say it. Yeah, I would take LAH, and what am I going to get when I react it with LAH? No. I'm going to get a primary alcohol, right? So I take an ester, LAH, I get a primary alcohol, and then what do? I oxidize it with PCC. I do a two-step process. The yields will be high. You do not have to have a whole lot of technique available to you to do this, okay? So, any one of you could take an ester, reduce it all the way to the primary alcohol with LAH, and then throw it in some PCC and oxidize it up to the aldehyde. And I'll even be honest with you. When I go into the lab and have to do something like this, I almost always do the two-step process. Because dibol is a pain. I got to keep it at low temperature. I got to watch it and babysit it. I can just take this, throw in the LAH, go to lunch, come back, isolate the product, throw it into PCC, go home, come back the next day, filter it off, and I've got my aldehyde. I don't have to sit there and watch it forever. So the two-step process is actually probably more forgiving of our schedules and other things than dibol is, okay? So another reagent that you all need to commit to memory, dibol, right? It can reduce esters to aldehydes. We can also reduce acid chlorides directly to aldehydes using this reagent here that kind of looks like lithium aluminum hydride. But how does it look differently? I see lithium, I see aluminum, and I see a hydrogen. But how is it different than lithium aluminum hydride? It's got some other stuff on it, right? What's that other stuff? It's pretty good size. 3 tert-butoxy groups, yeah? And what are those butoxy groups replacing that's on lithium aluminum hydride? No, lithium aluminum hydride. LAH, what's the molecular formula for LAH? Lithium, aluminum, and how many hydrogens? It had 4 hydrogens, right? So we've replaced 3 of the hydrogens on LAH with tert-butoxides, right? Does that make it bulky? It makes it really bulky, right? And it only has how many hydrogens per mole? 1. LAH has 4, right? So LAH can't stop at the aldehyde because there's still plenty of hydride around to do the next reaction. However, here, if I do this at cold temperatures, this still has to be done cold. If I take an acid chloride and I react it here, this hydride will attack the carbonyl, break the weak pi bond, and then as it warms up, this comes back down and the chloride leaves. And there's no more hydrogen or hydride around at low temperature for this to happen. So you can actually get an aldehyde out of that reaction. Pardon? You can't. This is the second step. After this has been consumed, then you quench it with water. So after the reaction's over, you can quench. But yeah, we wouldn't take this and mix it in with water at the same time. Neither with the dibol. Dibol will react with water. Okay? We can also make aldehydes by this two-step process. What is that two-step process? That is the hydroboration oxidation sequence. What does the hydroboration oxidation sequence give me? An alcohol. What kind of alcohol? Pardon? An anti-Markovnikov alcohol, right? And so you'll remember that when we had a double bond and we did this, we got an anti-Markovnikov alcohol, right? But I don't have a double bond here. I have what? I have a triple bond. And so when I do this, I end up with that. What is that? Let me write it up here. What is that? I won't call it conjugated. What would we say this is? An ene? And an alcohol is a? Enol. It is an enol. We talked a little bit about enols last semester. They do what? They want to change. They want to rearrange. They want to, there was a special word we used. It started with a T. Tautomerize. They want to tautomerize. And they will tautomerize into the aldehyde. And this is actually more stable than the enol form. Okay? So this undergoes an enol aldehyde tautomerization. Okay? And so we can make aldehydes also by the hydroboration oxidation sequence of carbon-carbon triple bonds. For the rest of the semester, let me just tell you, you've already learned everything that we need to know for this entire course. We're at a point now where we are taking what we have learned. It's true. It's true. We are taking what we have learned and applying it in different situations. You've already learned about hydroboration, oxidation. You've already learned about reducing agents. You've already learned about PCC. We're just applying them in different situations, okay? We also learned, right, that we can take alcohols and oxidize them. So here we have a secondary alcohol. We're going to oxidize that to a ketone. What are these reagents generally called? Those are generally Jones reagents, right? Jones reagent is technically chromium trioxide, sulfuric acid, and water, but we know that sodium dichromate or potassium dichromate will work. Even PCC will work here just fine on paper. It's just that PCC costs a little bit more than the Jones reagents. So we typically, practically, pick the other reagents. But PCC would get you full credit on a test, okay? We can also make ketones by reaction of acid chlorides with something kind of funny here to give a ketone. What is this? What is it? It's an organocuprate. What is it?
Copper.
It is copper. There is lithium. There are R groups.
And what?
It's kind of like a Grignard. It's an organometallic reagent, right? But it's not a Grignard. It's kind of like a Grignard. It's an organocuprate. Some people call them Gilman reagents. Don't worry about that. In a way, the copper is kind of a protecting group. The copper does not allow these R groups to add to carbonyls, to typical carbonyls. If we took a ketone and put a Grignard in there, it would react, right? If we put an alkyl lithium in with a ketone, it would react. Organocuprates do not react with typical carbonyl-containing compounds. They do other chemistry, okay? And we'll learn about that other chemistry more. There's more than they can do. But one of the things that they will do is they will react with acid chlorides and give us ketones, okay? Notice there are 2 R groups on this cuprate. Only one of them gets transferred, okay? Anybody want to take a guess as to how we make organocuprates? It's a favorite topic of mine. Did a lot of my postdoctoral work with organocuprates. or with cuprates in general. How do we make them? You don't have enough chemistry under your belt. Take a guess. How might you make an organocuprate? Nope. Nope. You all know how to make alkyl lithiums and Grignards, right? How do you make those? Alkyl halide and magnesium, or for the lithium reagent, lithium, right? So if we took an alkyl halide and lithium, we'd get an organolithium, right? It turns out that the way that you make these is you simply take an organolithium and add what to it? Copper. That's it. Yeah, so you take an organolithium, like, I don't know, methyl lithium, let's just say, and you drip it into a solution of something like copper chloride that has been dried. Obviously, it has to be dry because if there's water around, the organolithium will react with that. And it will form this organocuprate in the flask, and we call that in situ. So we don't actually make these and isolate them. We make them and generate them in the flask. And then we would take the acid chloride and we would drip it into our solution of organocuprate, and we would get a ketone after workup. Okay? Chemistry is pretty straightforward. You can think of these as just very weak nucleophiles. Okay? They are weak carbanions that will attack an acid chloride, but really won't attack a ketone. Okay? Why will they attack an acid chloride and not a ketone? Can anybody tell me? What do we know about acid chlorides? Are they weak electrophiles or strong electrophiles? They're stronger electrophiles, and why are they stronger? All right, so the carbon-chlorine bond is polarized, and chlorine's pulling electrons to itself. So what does that do to the carbon of the carbonyl? Gives it a lot of positive character, right? So it's a strong electrophile. What about a ketone? It's weaker, and why is it weaker? Yeah, they're not terribly polar, and you have that hyperconjugation effect, and you also have our favorite word, that steric hindrance, right? Steric hindrance. We know that ketones are the least reactive towards nucleophiles of the carbonyl-containing groups that we've been talking about, right? Here we only have one R group. Here we have two. So all of these things come into play, okay? We can also make ketones by Friedel-Crafts acylation, right? We learned that last chapter. What kind of chemistry is that? Other than the Friedel-Crafts acylation, that's the name. It belongs to a general reaction class called 3 letters. EAS, which stands for electrophilic aromatic substitution, right? So we can make ketones that way. We can also hydrate the alkyne. Notice here we're just using water and sulfuric acid, a little bit of mercury around as a catalyst. We get a ketone out of that. What's the intermediate? It is an enol, but it is a Markovnikov addition of the water, not an anti-Markovnikov addition. So if we take a terminal alkyne and we add water and sulfuric acid, we're going to get a ketone. If we take this same alkyne and do the hydroboration oxidation, we end up with a come on, an aldehyde, right? We can add water 2 ways. We can add water in a Markovnikov fashion and get a ketone, or we can add water in an anti-Markovnikov fashion and get a aldehyde, right? There are 2 places that we can react on aldehydes and ketones. The first and most obvious place is at the carbonyl carbon, right? We would expect that a nucleophile can simply attack the carbon of the carbonyl, break the weak pi bond, and we end up with an alcohol. However, the alpha carbon of a ketone or an aldehyde is also potentially reactive. All nucleophiles are what? All of them are Lewis bases. But not all Lewis bases are nucleophiles. Well, if we have a nucleophile that is really nucleophilic, it's going to do the chemistry that we see here. However, there are bases that do not behave as nucleophiles. Can anybody give me some examples that we've already learned about? Sodium hydride is a good one. What else? Potassium tert-butoxide. Very good. Those were the two common ones. What else? There were two other three-lettered reagents that we talked about. They started with D. DBU and DBN. Those were non-nucleophilic bases, right? Those are what we're talking about. If you take a carbonyl carbon, or excuse me, a carbonyl containing molecule that has alpha hydrogens, hydrogen atoms on the alpha carbon, a base can react with that and pull those hydrogens off and generate what's called an enolate. Why is that? Why can a base react and pull those hydrogens off? That's true, but why? Do you typically think about a base reacting with a carbon-hydrogen bond? Not typically. What's so special about these carbon-hydrogen bonds? Other than the fact that they are alpha to the carbonyl, which does have something to do with it. When we're trying to determine whether or not something is a good acid or not, what do we look at? We look at pKa's, but you don't have that in front of you right now. But what else do we look at? We look at the stability of the conjugate base. What can you tell me about the stability of this conjugate base? It's stabilized by resonance, right? These hydrogens are more acidic than you might expect, okay? And so you can deprotonate these alpha hydrogens pretty easily. And it turns out this is really good because you can take this electrophile, or excuse me, this carbanion, which now can react with an electrophile, and you can form new carbon-carbon or carbon-electrophile bonds. Okay, this is called enolate chemistry, and we'll be learning more about it in this chapter as well. Okay? Again, most of everything that you need to know, you know. But this is where things get a little more complicated because you're going to have to pay attention to the details. You're going to have to pay attention to the details. And even though you don't have a note card allowed on the next exam, I still think it's a good exercise for you to go through thinking about what you need to put on a note card. Okay? So we're going to stop there. On your way out, please put your inverted lecture up here where Alex is. Just make a stack. And I'll see you all on Wednesday.